those who don't know me, I'm Michiel from Vlag. I've been working for the HPP since last September, and I've been working on the automatic TVB model generation. I hope my screen is visible to all. In this presentation, I would like to introduce RateML. That's how we call the automatic TVB model generation workflow, which for now produces TVB models, only models for TVB and also CUDA models. All right. So what I would like to talk to you about today is what is RateML, how does it work, why do you need it, and which models does it produce. So I will be discussing a little bit the Python versus CUDA models XML implementation, because it's XML based. I will say a little bit about the parameter space exploration, which we do on the GPU. So the CUDA models which are produced or in this setting that you can do a parameter space exploration with it on the GPU. And I will talk a little bit about the current status. So RateML, it's a domain-specific language. Why do you want to use this? Because what we want to do is basically we want to abstract the programming from the modeling, so that the modelers need not to be concerned with the implementation of the models. They can just build their models and run simulations on it. With it, we based our domain-specific language on an already existing DSL, which is called LAMS. Basically, this is a brother of NeuroML, or it's a little bit more than a brother, because it needs LAMS if you want to work with your differential equations, with your drift equations. Then LAMS is a specification that has been designed for this. And also the constructs, which I will explain a little bit later, they coincide with the constructs also used for the rate model, so that was a good match. And LAMS is much more than just a DSL, because it's also a simulator. NeuroML, by the way, has been produced by Patrick Gleason. I have to mention that, because we're more or less surfing on his waves for LAMS as well. So basically what the model generator does is that it takes an XML file, and it's a human readable extensible markup language, as you can see in the bottom of this screen, as an example of a Kuromoto model. It has some constructs, constants, dynamics, which hold state variables and time derivatives, on which I will elaborate a little bit further on. So what we use is something called Mako templating. We read in the XML file, we translate it through Mako templating, which is a templating library for Python to efficient Python files, and also to CUDA C files. And basically, what we do now, I've tested with 5 different models, so we can now produce 5 models, 4 models that were already existing. I tested with 1 model that was already out there, the Montbrion model, and I checked this, and this is working fine, the translation. So for now, the Kuromoto, the epileptor, the generic 2D oscillator, and the other one I forgot. Well, these models I checked, and these models can be efficiently transported into Python code and into CUDA code. So now I will zoom a little bit in on how to use the DSL. Basically, the API is it's already integrated in TVB, in TVB root. So you can on command line you can just import this this package, the TVB package, and it will be already a part of it. And it's just a single function called templating, in which you can give your model the name of the model and just the location where your model is located, and then it will automatically translate the XML file that you give into Python or CUDA file. The constructs that are available in the XML are summed here. The only difference is that with CUDA you also have a parameter space exploration enabled, which has additionally three different constructs which aid in setting up the parameter space exploration. That are the parameters which define the parameters that you want to explore. Derived parameters, it's kind of a temporary variable that you can create using the parameters. And also a big difference between the Python models and the CUDA models is that you have to define the coupling explicitly in the CUDA files, which also gives the modeler a bit more freedom when using the CUDA models in parameter space exploration, because they can define the coupling themselves. And in TVB, this is a different class. So I will zoom into this constructs, to beginning with constants. So these constructs all build the XML file which you translate. Well, it starts with constants. These are just constant variables that you can define for the model file. And they have a few attributes, and some attributes differ when you use the Python constants from the CUDA constants. Different attributes, for instance, is the domain. For the Python models, you can enter a domain for the constant that you enter, which is then used in the framework and not explicitly in the non-framework versions of TVB. The CUDA constant doesn't have this, and you can leave a description as well if you want, but this is more for the user in XML than something is done with it in the model itself. Then we come to the dynamics. The dynamics hold the state variables, which you can define. And to keep the naming intact, I've used for state variables the default attributes to give us the boundaries for the state variables. This naming is also used in TVB. And in CUDA, I named it boundaries, such to make clear that but these are the boundaries that your state variable, when calculating, needs to be in between of. If we move to the derived variables, the next construct is the derived variables, which basically is a temporary variable that you can define. Making it more easier to state the dynamics of your model. And these derived variables, of course, as well as the constants you can use in defining your time derivatives, which I will come in the next slide. We also have conditional derived variables, which you can formulate if statement with. Basically, you can see here that the I dot is the name of the variable that you give. The condition is the condition your case has to uphold to, and then the cases separated by a comma are the if or else constructs, making it this is a very necessary construct as well, of course, to make if statements in your model. Then the time derivatives. These are the dynamics. These display the dynamics of your rate model. Here you can enter any formula that you would like, using the variables, of course, that you have defined, or the constants that you have defined before. And LAMMPS also comes with an interpreter for these time derivatives. So that's a nice given as well, because it does some checking on the formulas that you have entered in this field. For instance, it checks if the naming that you use is not an eigen name for programming a function, and if the formula that you entered is more or less correct. So two pluses it will not accept if it is next to each other. Then we have exposures, and basically exposure is, as the name says it, how your data is to be exposed whenever the kernel has run. Basically, there's a difference in between the Python and CUDA exposures. Python exposures also needs a default and choices. So the default will be always calculated, and the choices, this is also for the TVB framework. If you want to use this, then you have a certain range of choices which you can select. Mostly these are relations between your state variables, which it will then output eventually. And the same holds for CUDA. Basically, you give a name and a choice. And in the example here, you can see that, well, this name is how it is saved, and basically it will just output the state variable at the end of the simulation. And this is data, of course, you can use then to do validation on, or in case of parameter space exploration, you need these exposures, of course, to if you want to put this into a larger suite. Then we come to the parameters that are only used for CUDA. Basically, we have parameter and derived parameter, and the parameter, you can define the parameters that will be explored in the CUDA file. And defaultly for CUDA models, always the speed and the coupling are explored. But in principle, you can of course enter any variable that you want that needs to be explored in the CUDA file. And also you have a derived parameter, which is a temporary variable which you can give an expression relating to the parameter that you defined. Then let's talk a little bit about the coupling. As I said, in the CUDA files, you need to explicitly define the coupling as a component type. So the drift equations is a component where you specify your time derivatives, and also the coupling function is a different component type in the XML file as defined here. And for this component type, we can reuse the constructs that are already which I already described above to express the coupling functionality with. And here in the dynamics, you see that there's a pre and a post coupling function defined, which basically results in pre times post, which in the end result, it will be the CPOP1 is the coupling of population 1 that which gets this result. And you can also add an expression to this result if you want to even try to you want to give another relation to this expression, to this calculated coupling functionality eventually. You can for the CUDA motor, for instance, there's only one state variable, and there's only one coupling functionality as well. But for more complex models like the epileptor, for instance, you can also, if you want, define more coupling functionality, a different coupling functionality. I mean, multiple coupling functions inside your model. So these constructs give the user a little bit the freedom to of a lot of freedom to define their models within the limits of the rate models that TVB uses, without having knowledge of the programming constructs that lie in the background. And basically we can build any model that you want from the XML file. You can translate it either to Python or to CUDA. And well, then I'll zoom in a little bit about the parameter space exploration, the CUDA files, the CUDA models that we produce. The theory behind this and has not done by me, but it has been done by Marseille University and mainly by Marmaduke and Jan, which did a terrific job in forming the GPU models, because it's a very brilliant code, if I would say myself. Basically, what it does is that it spawns a network of threads, of course, like we are used on a GPU, but every thread in itself is a TVB simulation. Every thread executes a TVB simulation for a combination of parameters that are entered. So that's really nice. With one GPU, you can, well, depending on your grid size, of course, you can do your grid size number of simulations simulating certain parameter combinations. And well, this is the calculations, as Michael Schurner also said, are not very complex. So therefore, it is the GPU is a very good backend for these kind of calculations, and also, but yeah, the bottleneck for this application is the memory fetching, because a lot of memory needs to be fetched, or relatively a lot of memory needs to be fetched, because when you talk about TVB simulations, you also have a delay, of course, between your nodes. Meaning that for the GPU that it has to fetch the results from previous simulations from memory as well. I am currently in the process of benchmarking the DSL. I've been looking also not only at capacity, but also not only on performance, but also on capacity. And I have some preliminary results they're mentioned in the table. For instance, on the Kuromoto the simpler model, we can do 10,000 parameters combinations of two parameters, so 100 times 100 different parameters, which we can simulate in roughly 55 seconds. And but we see that if and this is done for 40 seconds of brain time on the V100 GPU. If we go a little bit more complex to the Epileptor, for instance, which has 6 state variables and needs a lot of more GPU memory to be stored, we can only do 10,024 parameter combinations, and in roughly the same time, roughly 55 seconds. But as I said, these are preliminary results. I have to look at how the memory is spent on the GPU. And maybe we can crank it up, or maybe I have to tune it down. But this is some preliminary indication of what is possible with these CUDA models. Then, what is the current status of this whole project? Well, the DSL and the Python code are now merged into the main branch of TVB. Yeah, the CUDA generator is currently under revision. A PR is currently pending for the TVB HPC repository, and will eventually, hopefully, also find its way to the TVB root main repository. We have documentation in the repositories and code 1. And some Jupyter notebooks as well. You can find there, run some tests. Also, we have on TVB, there are examples as well on how to run the CUDA and the normal TVB models. Yeah, we're working on, as I said, on benchmarking, also looking at numerical errors and in comparison between the different kernels. Basically, what we're doing is we're trying to mimic the regular TVB models in an MPI environment where we just spawn as many threads as that we can do on a GPU, and try to compare these things together and see what we can learn from it. The noise graph curation is pending at this moment, and it has already been used by IM7 and by Clergy Paris University. I think Thanos Manos is the one who was using this code already. Yeah, as I said, well, benchmarking is in progress. We're doing this multi-node version on the deep cluster. We're testing on, as I said, on CPUs and on GPUs to compare functionality, not only performance but also looking at capacity and errors then also. Yeah, for the future work, of course, yeah, generating your models with RateML, you can of course use it always in every application that you use for TVB. Whenever new models need to be generated, you can use RateML to generate these models. But yeah, especially for code simulation, for instance, that could be something that DSL is going to be used for. And yeah, we're also looking at to complete the whole parameter space exploration stuff into a learning to learn framework. Yeah, which basically is a machine learning type of algorithm, which will also search for a certain optimal set of parameters that you're exploring. Because now basically the CUDA version is just crunching numbers, but yeah, it's crunching it pretty fast, I would say. And if we put this into a machine learning type of environment, that would be even more awesome. And yeah, also in Marseille, I know that Marmaduke, I spoke with him about it. He's also working on this kind of framework using Stan, as we saw also in the previous presentation being explained. Well, that basically is the current status of the DSL. Still going, and yeah, in the end, I would like to make some acknowledgements explicitly. Well, I already mentioned Marmaduke and Jan, which are in Victor Yersas group in Marseille. Yeah, Thanos Manos, Simon Eickhoff from INM7, and Sergi Paris. Also, you, Petro Ritter. I see that the code was also developed as part of the CDP8, the HPP. And Alexander Pais, who had also a fundamental role in the early phases of the project. Thanks.